So what have we done so far? Our factoring polynomial stuff. We started off factoring out greatest common factor. We do that every time we can. Of course, phones should be away. I should not see anybody on phones out there, please. Chromebook should be all clicked closed, and books should be up here. We started off by looking at factoring by grouping, which is how we deal with four-term polynomials. That's our strategy for factoring four-term polynomials. Then we reviewed how to factor trinomials, right? So there's our strategy for factoring three-term polynomials. What's left? Yeah, two-term polynomials, right? So how do we factor two-term polynomials? Well, the answer is with binomial factoring patterns. So first of all, let's look at what those patterns are. So here are the patterns. We've got, we're only going to look at two layers of binomials. We're going to look at the sum and difference of squares and the sum and difference of cubes. In other words, something squared plus something squared minus something squared, something cubed minus something cubed plus something cubed. And good news, there is no sum of squares pattern. A squared plus B squared is a pattern that does not factor. And so if you see something in the form A squared plus B squared, you're done. You cannot factor that any further, okay? But the other ones all can be factored further. We've seen this guy already, right? We looked at this the other direction. We said that the conjugate product pattern, didn't we say something like A plus B times A minus B is equal to A squared minus B squared? So we went in the multiplication direction. Now we're just going to flip that around and reverse it and do the factoring direction, go in the other direction. So if we see something that looks like the pattern A squared minus B squared, which we call a difference of squares, difference means subtraction, right? Then we know that's going to factor into the conjugate product pattern, right? So it factors into a product of conjugates. So that one we already know. The cube ones, I don't know, have you guys ever seen these before? Probably not. Sum and difference of cubes patterns? I would guess you have not. Okay, there is, so you're going to memorize these, but there's some things about these that make the pattern easier to memorize. Okay, for one thing, notice that if I've got a difference of cubes or a sum of cubes, notice what the structure looks like when you write this as a product of factors. You get two factors. You get a binomial factor and a bigger trinomial factor. The terms in the binomial factor are just A and B, right? So that's easy. You know this is going to be an A, that's going to be a B. We've already identified what A and B are when we're looking at these patterns, right? A is the thing that's being cubed in the first term. B is the thing that's being cubed in the second term. So the first binomial just involves the terms A and B. What about the trinomial? Well, the trinomial is easy to remember too because it's all the three different ways that you could multiply A's and B's. A times A is A squared, A times B is AB, and B times B is B squared. Okay? So you know what the terms are going to be before you start. All we have to do is just fill in these operations. What are the symbols there? Are they positive? Are they plus or minus? The last symbol is always plus. The only two that ever change are just the first two symbols. And here's the pattern. Whatever you start with here, if it's a difference of cubes, well then, then this becomes a minus. That becomes a minus, right? The first term is the same as what you start with. In the binomial, you get the same as what you started with. And the second one, second symbol, is always going to be its flip. Okay, make sense? So a cubed minus b cubed would be a minus b times a squared plus ab, and you always end up with plus b squared. So what's this going to be down here? What's this guy going to be?
A plus b.
Yeah. That one's a cubed plus b cubed is going to be a plus b times a squared minus ab, and you always finish out with a plus b squared. Okay, make sense? So there's the patterns. Now, some important things about these patterns. So the trinomial factor that you get, the big trinomial factor, is never going to be factorable. Okay, it's always going to be what we call an irreducible quadratic factor. It's this stuff we haven't really talked about yet, so a lot of this we can ignore for now. We don't know about, we haven't reviewed discriminant yet, but we know it can't be factored. And here's the other thing that we haven't talked about yet, but it's important. Its zeros will never be real numbers. They're always going to be non-real numbers, imaginary numbers, which we haven't talked about yet, right? But eventually that'll become very important to us. The big thing for us right now, though, is it can't be factored, and it has no real zeros, which we'll talk more about, very soon. Okay. All right, let's try this. Today, all we're focusing on is just the factoring part, though, just getting it into this pattern. So what about something like this guy? Which pattern is that using? Yeah, that's a squared minus b squared, isn't it? Okay, that's the pattern a squared minus b squared. I don't know why I did that. I guess I can leave that there. A squared minus b squared. And so what does that give us? Is there anything up here? Can't remember. So what's my a? X. Okay. What's my b? 4. Okay, and if it's the a squared minus b squared pattern, then I'm just getting, I know that that's got to be an a, and that's got to be an a, right? That's a b, and that's a b. And what are the signs going to be?
Negative and positive.
Negative and positive. And it doesn't matter the order, right? I can flip it around if I wanted. X minus 4 times x plus 4. Easy, right? No big deal. Okay, how about this one? Same kind of thing, right? Doesn't that fit the a squared minus b squared pattern? What's a going to be this time?
3x.
Everybody see that? What could I square and get 9 times x squared? I'm squaring the quantity 3x. And then obviously b is 2. Okay, so then doesn't that just give us 3x minus 2 times 3x plus 2? Right? Okay, give me thumbs. You've seen this before, right? Okay. What about this one? 4x and 3y, yeah. Four x and 3y, and 4x minus 3y times 4x plus 3y, or vice versa, doesn't matter. Okay. What about that one? Okay, yeah, what could I square to get x to the 8th? X to the 4th, yeah, good. What would I square to get y to the 6th? Y cubed. Then we just follow the same pattern. Okay. Thumbs? How about this one? Okay, so we could rewrite this as x squared minus 9 squared, which is going to factor into what? X squared minus 9 times x squared plus 9. Good? We done? No, what can I do? Yeah, look at this guy right here. So this one, I could think of the 9 as being a what? And then I've got x squared minus 3 squared, right? So that's going to break up into what?
X minus 3, x plus 3.
How about that one? Can I do the same thing?
Or,
It is x squared plus 3 squared. So what's the sum of squares pattern?
oh, there's none.
There is none. So that one's done, right? That one we can't do anything with. So there's our answer. Now it's full. It's completely factored. Okay. So this, for your notes, I just threw that in there. We just did that stuff though. So what about this guy?
Archie, raise it higher.
6x minus 8.
Raise it higher, Archie.
Okay, so you told me we could make that 6x. I don't know why I even included. We probably don't need this one, right? 8.
You raise it.
Oh, I know what it was. Yeah. Okay.
Go.
I know why I did this one. What do you think?
On that last one, why couldn't you just write it as the positive 1 cubed? Why couldn't you just write it as what problem were we in?
That one right there?
Yeah, why couldn't you just write it x plus 3 cubed and then with the x minus 3?
Okay, because you mean combining these two, you mean?
Yeah.
Well, for one thing, that's a 9. It's not a, you're thinking about making that an x squared plus 3 squared. I see what you're thinking. You're thinking this. Okay, let's talk about why this doesn't work. I see your question. Here's the question. X plus 3 times x squared plus 3 squared. Okay, this thing right here, x squared, here's why. X squared plus 3 squared, that is not equal to x plus 3 quantity squared, right? They're different. X plus 3 quantity squared would be x squared plus 6x plus 9, right? And so I can't combine those. If this were x plus 3 quantity squared, multiplying by another x plus 3 would be x plus 3 cubed. Okay, that makes sense? But I can't combine them that way. If I were to multiply these out, let's just see what would happen. If I were to distribute these, I would distribute that x, which is going to give me an x cubed. Distribute the x there, and I get plus 9x, because that's just 9, right? Distribute that, and I get plus 3x squared, and distribute that, and I get 3 cubed, which is 27. But I get all these cross terms in there that mess it up. Okay, that makes sense? Okay, good question. Okay, so everybody agree with that?
I do.
Okay, so what's that become then?
6x minus 8, 6x plus 8.
Are we done?
We reduce it, right?
Oh yeah. What could we do there? What could I factor anything out of this guy?
A 2.
Okay, so I could factor this one into 2 times x, 3x minus 4, right? Well, how about this one?
No.
Wait, yeah.
Yeah.
Yeah, I could take another 2 out times
Oh, yeah.
what?
3x.
plus 4.
3x plus 4. And then how would I write my final answer?
4 times x.
Okay, good. Yeah, I could take these two right here. The 2 and the 2 out front would make a 4 times 3x minus 4 times 3x plus 4. Okay, all that was unnecessary. How come? What did we do wrong?
Didn't take out 4.
Yeah, at the very beginning, what we should have done, what's our first step? Always when we factor.
Find the GCF.
Find the GCF. What's the biggest number that divides into 36 and 64? 4.
Wow.
Yep. So I could have written that as 4 times what?
9x squared minus 16.
Aha. And then what is 9x squared minus 16 going to split into by my difference of squares?
3x minus
4 minus 4.
Way easier, right? So always factor the GCF out first, every time. Okay, so how about something like that?
You can't
Let's
take,
just not do that.
there's no GCF.
No, we got to do that.
There's no GCF, I know that.
There is no GCF, you're right. That looks like, it looks like if I write this in standard form, I would put the x to the fourth term first. Okay, so could I, there's something, I don't know if did I talk about the step down? Like when we were looking at the factoring by grouping, we talked about the coefficient test, right? Right? A over B has to equal C over D for it to, okay, did we talk about the step down issue too? Like the variable has to step down by the same amount in each?
Yep.
We did, okay, good. So either way though, that's a four-term polynomial. It's not it fails both of those tests, right? Because A over B does not equal C over D. Negative 1 over 1 is different than 20 over 100. And the x's step down by 2 in the first group, and they step down by 1 in the second group. So give me thumbs. Is factoring by grouping going to work? No. No chance. So we seem to be stuck on this one, right? Okay. So we just throw up our hands and move on. No, there is a way we can do this. Here's my hint. Look at that trinomial part. That looks like a quadratic trinomial. Can I factor that? What would the magic numbers in that trinomial, if I'm going to factor it, what would they have to multiply to?
10.
They're the same one twice, right? So that factors into x plus 10 times x plus 10, agreed?
Yeah.
What's another way of saying that?
X squared, x plus 10 squared.
X plus 10 squared, yeah.
Wow, you're actually. Really?
Okay, give me 1 to 5 on that. Everybody see what we did there?
See.
Okay, when we factored that, because it was a perfect square trinomial is what we call that. Perfect square trinomial is one that factors using the same magic number twice, which means we're always going to end up with a single factor times itself or a single factor squared. Because that trinomial was a perfect square trinomial, this is going to work out. Look, I end up with x plus 10 quantity squared minus x to the fourth. Now that does fit one of our binomial factoring patterns. Which one?
A squared.
A squared minus b squared. Yeah.
Wow.
Look, it fits. This fits the pattern x plus 10 squared minus x squared, doesn't it?
Yeah.
Right?
It would.
Okay, and so now we've got that binomial factoring pattern. What's this thing going to break up into?
Plus 10.
Okay, good. That's my A, right? This whole thing here is like my A. And that thing is like my B, right? So A plus B is going to be x plus 10 plus x squared, right? Everybody agree? Okay. A minus B is going to be x plus 10 minus x squared, right? Okay, so what should I probably do then? Like, let's just see something here. So do I need those parentheses?
No. Oh,
Are they accomplishing anything?
no.
How come? You're right, they're not. How do I know I can just erase it?
Because you do exponents before you do addition.
Could say it again?
You do exponents before you do addition.
True. How come I can just erase those though, around the x plus
Is there
10?
a plus sign after? There's no way.
Okay, nothing's being distributed, right? And there's no exponent up there, so they don't serve any purpose. They're just, why are they there? They're just there because the x plus 10 was grouped in the previous step. That's the only reason, right? We can get rid of those. So how about if we get rid of the parentheses, and while we're at it, let's write this trinomial in standard form. X squared plus x plus 10. How about this guy over here? Same thing. We could write that as negative x squared plus x plus 10. Okay. Are there any magic numbers that multiply to 10 and add to negative 1? No, right? Now, this one here is a little bit tricky because I've got a negative in front of the x squared. So technically, we'd want to use factoring by grouping with this one, right? We want to be able to find magic numbers that multiply to A, which is negative 1 times C, to multiply to negative 10 and add to what? 1. Are there numbers that do that? No. So we can't factor that any further. We're done. But we had to check, right? It's possible that maybe we'd end up with something here, trinomials that could be factored further. But we can't, so we're done. That's prime. Okay? Give me 1 to 5 on that one. That's a tricky one, right? I get it. That's a tricky one. Moving forward, what's the only way you could look at this? It's like playing chess, right? As you get further into algebra, you got to think more steps ahead. The only way this could be done, could be a difference of squares, would be if that trinomial just happened to factor in such a way that it's a perfect square trinomial, right? If it wasn't, if that had been x squared plus 30x plus 100, there's nothing we could do. Okay, we would have just been stuck with the original because it wouldn't have factored into something squared, which meant I would not have had that difference of squares pattern to rely on. Okay. How about that one?
We could actually factor something out GCF.
GCF, there you go.
You could take out a
12.
12.
You took out a 12.
12 actually.
Times what then?
X squared plus 4.
Okay, now what?
We could do it. You could get an X
Say it again.
squared.
That's sum of squares, so
Yep.
we're done.
I didn't know it was
Right?
12, but
If you have something squared plus a number, the only pattern it could fit is sum of squares, which is a non-pattern. Doesn't do any good. So we're done. That's it. All we can do is factor out a GCF. Okay, let's move on and take a look at our sum and difference of cubes patterns. So what about one like this? What if I want to factor x cubed plus 1? Okay, so the first step is we want to see that this does fit a pattern, right? Everybody see that 1 is the same thing as 1 cubed. So it does fit the sum of cubes pattern. What's our A? What's our B? 1. Okay. Okay, so then now we want to see if we can fit that pattern. Okay, so then what is the pattern? A cubed plus B cubed equals A plus B, A squared minus AB plus B squared. There you go. Good. Okay, and now we just fill in A and B and we're done, right? So that's what we get. Make sense? Okay. Is there any chance we could factor that trinomial? Should we try? No. Remember, it's never going to work. Got to go way back. Man, that's way back. We did a lot. How about that? It's never going to work. These are always irreducible quadratic factors. You can try until the cows come home. They're never, ever going to factor. Oh, there we go. Okay. So that's our answer, as far as we can go. How about this one? Same thing, right? What's the pattern?
X squared, A squared, B squared.
So what's
Cubed.
A minus B, good, times,
Squared plus AB plus B squared.
good. Okay. And then all I've got to do is just plug in my values of A and B, which are just x and 3, right? X cubed plus 3 cubed. So there's our answer. Okay.
We factor out GCF.
Ah, yes. What's my GCF? Y cubed. And then this looks a lot easier. It looks terrible at first because you got x's and y's in there. But my GCF is a y cubed, which leaves me with
64 minus
I
X
got a GCF value.
okay, what pattern does that fit?
A squared.
No.
A cubed.
Cubed. Oh my
A
god.
cubed minus B cubed.
Minus b cubed, what's a then?
4 cubed.
Aha, okay, 64 is the same thing as 4 cubed. So this is gonna equal, I've got my GCF out front. And this thing's gonna split up into what then?
4 minus x
Times,
4 squared
aha, okay, good. A squared, which is 4 squared, 16
minus
Plus.
x
Plus.
plus x plus x
plus,
x squared.
plus, no, it's this is the difference of cubes pattern, right?
Plus AB,
So AB would be
4x.
4x, there you go, plus,
Wow.
X.
Really cool.
squared, right? And how come? Let's write the pattern down, because we're just following the pattern. A minus B times A squared plus AB plus B squared, where A is 4, right? And B is X. Okay, make sense? Okay, so that's our answer. Okay, for our notes, there's a little more detail. Okay, last one. How about this guy? Now, this is really kind of cool. This tells you, this is something that's not covered in any of these textbooks, but this is a pretty interesting pattern that I want you guys to be aware of. So what if I wanted to factor x to the 6th minus 64?
Could you like take out a power of 3? Like
What can I do?
take out like a
GC.
power of 3, like the I don't know.
Just take out.
I mean, I've really got, does everybody see that I have two options here? I could think of this as a difference of cubes or a difference of squares, right? Because if I think of it as a difference of squares, a squared minus b squared, what would a be? What squared is x to the 6th?
X cubed squared.
X cubed. What squared is 64?
X squared.
Okay, so there's a squared minus b squared, right? I could also, turns out that x to the 6th and 64 are also perfect cubes. What cube is x to the 6th? X squared. And what cubed is 64? Well, 4, right? Okay, so does it matter? Probably going to end up at the same place, right? What if we start off with a difference of cubes pattern? A cubed minus b cubed. What's that going to give me? A cubed minus b cubed factors into what?
X squared plus.
We'll just do it A's and B's first. A cubed minus b cubed is
A minus
b times
A squared plus AB.
A squared plus ab plus b squared, where a is, here's my a, right? A is x squared, b is 4. So let's just follow that pattern. Okay, so we get that, right? A minus b times a squared plus ab plus b squared. X squared minus 4, that's a difference of squares again, isn't it?
Wow.
So I can break that down. But what's the problem here? Well, now the red factor is an irreducible quadratic. So by definition, we're done. Can't go any further. Okay. So is there a problem with that? Yeah, there is. The problem is, maybe there's a problem. We haven't learned this yet, but this is coming down the pike here in a little while. The fundamental theorem of algebra tells us, which we'll talk about later, but I'll mention it now, tells us that the degree of a polynomial tells us how many total zeros that thing has. Now, they may not all be real. Some of them may be non-real zeros, which we don't even know about yet. But this thing has a total of 6 zeros, including the real ones and the non-real ones that we'll talk about later. Okay. We only found 2 real ones. And then look, I'm stuck with this 4th degree irreducible quadratic factor that we can't do anything with. We're stuck. Now, if all of those zeros are non-real, we're okay, because we're not gonna do anything with them now anyway. But it's possible that maybe they're not. I can't go any further though, because when we use the difference of cubes pattern, the trinomial is a dead end. It's locked up. There's nothing we can do with it. Now, what if we had started off with a difference of squares instead? A squared minus b squared is what? What's the pattern? A squared minus b squared is a minus b times a plus b. Okay, so we get that, right? A minus b. A is x x cubed, right? B is 8. So x cubed minus 8 times x cubed plus 8. Okay, so now what?
Difference of cubes.
Difference of cubes. That's x cubed minus 2 cubed, right? And x cubed plus 2 cubed. Okay, well, those are patterns we know. Isn't this guy going to give me a is x, b is 2, so I get a minus b times a squared plus ab plus b squared, right? Here I have a cubed plus b cubed, so a plus b times a squared minus ab plus b squared. And look what we get here now. This is better. Okay, and you may not see why it's better yet, but it is going to be better because I get the same real zeros. I get these two irreducible quadratics, but later on in the year, you guys have used the quadratic formula, right? In the past. When I want to solve, when I want to set these equal to 0 and find the zeros of those other factors, yeah, they're going to be non-real, but I can just use the quadratic formula to find all of those. I use it twice. What am I going to do here? There is no fourth degree polynomial formula to lean on, right? I'd have to use the quadratic formula twice, which is a horrible mess. You end up with nested square roots of square roots. That's horrible, right? So what's the moral of the story here? There is a moral to the story. We'll come back and talk about this again later when it has more meaning. But whenever you have an option of using either difference of squares or difference of cubes, which one should you always use first?
X squared.
Difference of squares. You always want to lean on the simpler pattern until you no longer can, right? If you can keep using repeated patterns, you always use the difference of square patterns over and over until you're done with it. And then if you have to, you rely on the more complicated patterns. And later on in algebra, I promise you, that will head off some problems. Yes, sir.
Why on the a cubed minus b cubed couldn't you just square root the first factor, like where the irreducible quadratic?
Right here, you mean?
Yeah.
What do you mean square root it? You mean square root it to
Like
undo all those?
like you put x, or the square root of x to the fourth plus the square root of x or 4x squared and then plus the square root.
Okay, because the problem is, here's the deal. The square root, I'll show you why. It's a good question. The square root of a squared is equal to, technically it's equal to the absolute value of a, right? But it undoes the square root, you're right. But what's this? The square root of a squared plus b squared, is that equal to a plus b? It's not. It's not equal. And the proof of that is because a plus b quantity squared is not a squared plus b squared. See what I'm saying? So you can't just square root that. And we'll see that later on. We'll see that. Here's another proof of that that'll make sense. You guys probably already know this. If I can say a square root is the same thing as what fractional power? Have you guys talked about that?
Maybe.
The square, in other words, the square root of x is the same thing as x to what power? 1/2. We haven't talked about that yet, but we'll review that soon. So I could rewrite this as the quantity a squared plus b squared to the 1/2. But with our rules of exponents that we talked about, can I distribute an exponent when things are being added? No, only when things are multiplied or divided, right? So there's another way of illustrating why you can't do that, because I can't just distribute that power, which would be the same thing as square rooting each term separately. Okay, good question. Okay, anything else? All right, I think I'm done with that stuff. So you guys, the assignments are up. You can work on them. I'll give you a chance tomorrow to kind of work on that stuff. You may. You betcha.
So you send me that thing.